Alright, silly people, here's the situation. Remember back in chapter 2, whenever you were solving for reflection amplitudes and scattering amplitudes and that sort of thing for different situations, different potentials. Um, so this problem is kind of talking more about that, but turning it into a linear algebra equation where the vector BF is equal to something called a scattering matrix times the vector AG, where B, F, A, and G are all just constants that you just attach to your exponentials on it's A and B on the left side of the scattering and F and G on the right side of the scattering, right? Um, and so uh, the idea with this is if you can get your equations down to the form, and I'm just going to do the matrix multiplication here of S11 times A plus S12 times G, and F equals S21 times A plus S22 times G, then you can construct a scattering amplitude matrix, and it just is going to look nice. Um, yeah, so the first part of the problem is to do this for the delta function well. And if you go back to that part of the book, actually, which is what I'm doing right now, you get a couple different equations which describe the relationship between f and g and a and b, right? You get this guy, which is equation 2.136, f plus g equals a plus b, and also f minus g equals a times 1 plus 2i beta minus b times 1 minus 2i beta, where beta is defined as physical constants. It's the mass of the thing that you're shooting into the potential divided by h bar squared, k, where k is the momentum of the thing that you're shooting into the potential, right? Um, so we need to put these two equations into a form that looks like a and g instead of a and b on either one. So let's do this first. If we call this equation 1 and this equation 2, then let's just add the two equations together and see what happens. Well, on the left side you would get 2f, and then plus g minus g makes 0. On the right you would get a plus a times 1 plus 2i beta plus b, and then minus b times 1 minus 2i beta. This a and this a will add up, so you get 2a plus 2a times 2i beta, or 2a times I beta, I guess. But then these b's cancel out, so you get b, it's just plus b times 2i beta is equal to 2f. And then if you divide the equation by 2, then you get f equals a times 1 plus I beta plus bi beta. But it's still not in terms of just a's and g's. So what we're going to do is we're going to use the first equation again, but solve this for b this time. So f plus g minus a will equal b. Plug that into this guy now, so you get f equals a times 1 plus b, or plus I beta, plus f plus g minus a times I beta. And then we can move the f to the left side of the equation, so we can have f times 1 minus I beta, right? But then you have a plus ai beta plus gi beta minus ai beta. So the ai beta stuff will cancel out, and you get a plus gi beta on the left side, or on the right side, I mean, But now you can divide both equations by 1 minus I beta, and you get F equals A over 1 minus I beta plus G times I beta over 1 minus I beta. So this is going to give us S21, just going by our linear equations up top, and this is going to give us S22. Glorious. So we can go ahead and what else do we need? We also need S. We need B in terms of A and G now. So let's go back to this equation, which I used to solve the second guy, and plug in what we just got for F into it. So that was F plus G minus A equals B. And then this F is now A over 1 minus I beta plus G I beta over 1 minus I beta, and then also it's plus G and minus A should be equal to B. We can add these together if we give everything the same denominator of 1 minus I beta. So this is going to be A plus, and it's going to be minus A times 1 minus beta. So I beta minus 1 times A over 1 minus I beta. And then plus G I beta, and then plus G times 1 minus I beta. So plus 1 minus I beta there, and then 1 minus I beta here. That's going to be equal to B. Well, this A is going to cancel out with that A, and so you're going to be left with A times I beta on the fraction on the left, and then plus G, this I beta is canceled out this I beta, so you can get 1 minus I beta equals B. So that's going to take care of now S11 and S12, which means now we can finally write the S matrix, just putting in the values that we got into a big old matrix. S11 was I beta over 1 minus I beta. S12 was 1 over 1 minus I beta. And then S21 was just, where did that go? It was 1 over 1 minus I beta. And then S22 is I beta over 1 minus I beta. Cool. We can simplify that greatly if we just pull out the 1 minus I beta thing, though. So you get I beta 1, 1, I beta. Isn't that nice? The next one is we have to do the thing for the finite square well. So again, just going back to that part of the chapter, let me grab the relevant equation. Where was that? Okay, here it is. It's equation 2.170. It's B equals I sine 2LA over 2KL, L squared minus K squared F, and also F equals e to the minus 2I KA times A over cosine 2LA minus I K squared plus L squared over 2KL sine 2LA. Right, there's a lot more terms on these guys, but that doesn't mean that the problem is more complicated. It's just more writing. But we do need B in terms of A and G, not in terms of F. So let's go ahead and plug in F into the B equation. So we get B equals I sine 2LA L squared minus K squared e to the minus 2 I K A F. No. It's A now. And it's all divided by 2KL cosine 2LA minus I K squared plus L squared sine 2LA. Cool. So it's actually these two equations which we're going to zoom in on to find the matrix elements. And Griffiths suggested in the problem's hint that we need to make or take advantage of the symmetry of the problem. And what he's talking about is that these equations were found by setting g equal to 0, actually, but that's just an arbitrary thing that you have to do if you're only considering scattering from the left. But if you're scattering from the right, then you know that this coefficient that is multiplying a in the b equation has to be multiplying g in the first. So if you stick this guy here, but then you have it being multiplied by g, and also due to symmetry, this coefficient that's multiplying a in the f equation will now in the b equation be multiplying g. So just going to stick that there. And now we have both of the equations that we need. We've made use of the symmetry to get, this is going to be S11, this is going to be S12. This guy up here, I don't know where I'm going to put this, but that's S21, and then this constant here is S22. So we can go ahead and write the S matrix already. I'm going to do it in the more simplified form already because I don't want to write all of that garbage again. But both of them have to be divided by, and actually all of them have an exponential on it as well. So it's all times e to the minus 2ika cosine 2la minus I k squared plus L squared over 2KL sine 2LA. But then the S11 term also has a sine function multiplying it, so an I times a sine 2LA multiplying it, and also times L squared minus K squared over 2KL multiplying it. The S12 term is exactly just the prefactor, so that's a 1. The S21 term also is just the prefactor, so that's 1. And then finally, the S22 term is identical to the S11 term, so I'm just going to copy this down to this element here. And that is your scattering matrix, however much use that is to you. All right.